Okay. Starting another live stream for uMyo, the machine learning side of things. So last time we did some prep work with uMyo, and I kind of took some of the code that I got done for OpenMuscle, and we're going to be using the same type of machine learning, which is a random forest regressor. And so in order to do that, we're going to have to get some stuff done first. So today I'm going to just stream the progress that I do, trying to consolidate some code, work on it. It's a good time for you guys to chat with me. So leave questions or comments in the chat. I kind of just work on this whenever I have time. And I'm really excited because I'm pretty close to actually being able to capture labeled data from uMyo and actually seeing if we can use it to predict machine learning algorithm and to predict finger movements. So this is exciting for me. So I got some stuff set up. I actually really don't. I have mostly my coffee. So let me get everything ready. So first off, we have the uMyo base station, which we're going to use. But let me get the sensors. Oh no. Oh, this is kind of a bummer. No worries. You can't see me anymore in a picture-in-picture, but that's okay. So we have the LASK system. We have our uMyo band. And I have Diodario. And we have our spare battery. So I believe our battery is good. I might actually solder something today to make the double female side of the JST plugins, because the battery that I got has the opposite polarity, and it's also too big for the JST plug, so I'm just using a header pin here. But that should be fine. I'm just gonna double check that my microscope is working, which it is. So we can go ahead and place that. You can kind of see how the polarity of this is the opposite of this. Yeah, if they're lined up on the right side. But these are different size JST plugins anyway, so I've just been plugging them in like this. The uMyo for the time being. Okay. So I think I have everything. Perfect. So let's take a look here. And from Big Me, copy over to the left side. Okay, so now you should be able to hear me. So I had it kind of messed up, so I do apologize for that. I tinkered with stuff just before I started the stream, and that's usually a good idea, right? So, two folders I'm going to open up. Going to open up the code that I have that I worked on yesterday, and that basically just read the serial, and I created my own uMyo tools here, so you can see all the stuff I'm working on. But let's open up serial read. This is the Python program that I made, and we're going to open it up. Okay. Serial read. So let's just double check that this works. So first off, we are going to do some basics. We're going to get the base station plugged in. And we do so, we see that it does light up green and blue. And I will put this in the, so you can can see it here. I'm going to use a piece of cardboard, so I think there's a metal backing of this. Use my cell phone as a cable holder. That works. Okay, so D1, D3 are lit. I don't think that will change too terribly much. My phone is going to fall off the desk here. Okay. So I'm going to plug in one of these uMyos, like so. And I'm just going to turn on this first one. Turns red and it flashes green, and green means that it's in the USB receiver mode, and we do see that the D2 light lights up on the base station. So I'm using the USB base station, and there has got to be an easier way to clamp this. I have clamps. When you need a clamp, well, that's be very There we go. That's better. Okay. So, now that we have this going, we should be receiving packets. So let's go ahead and go to serial read. We're going to run this, and it says it sees some COM ports listed here. You could probably barely see that. Yeah, it says some COM ports are listed there. Anyways, so I'm going to select COM port 6 by hitting 1, and it is receiving data. That's great. So it's getting the data from the uMyo. That's perfect. Now, the 3D6 did edit some code for this, so let's take a look at what they did. I'm going to go ahead and stop this. And let's open up my downloads, the new code. And we'll see what this is. I think this one is just display stuff. So we're going to close this, open with Python. We're just kicking the tires here. And so it exited out, which is just fine, because I think you have to do it in a couple of methods, which that is just fine. I'm going to use the code I did yesterday because I made some progress. So we're going to stick in the uMyo tools. And I won't be messing with the new code that 3D6 has just yet. I will take a look at it, but I wanted to get this. So what we did yesterday is we did a uMyo data structure. So we took the code and we wanted to glean the information from it, right? So we're able now to pull out the information for each packet, because we want to record this and record it into a CSV file. So how we're going to do the machine learning is we're going to take our sensor data, which there's going to be 4 sensors. So we'll probably take the EMG signal, and it supplies 8 per packet. We'll probably try to take the accelerometer too, depending. We don't necessarily need it, but it might be helpful. And a time stamp of some sorts, because we need a time stamp and kind of an incremental measurement, something to tell us exactly how much time is passing. Because we're going to need to sync these up with the LASK system to label it. So a lot of the difficulty we're going to have is actually finding data that we can sync together in a single line. Because if I'm getting more packets from one than the other, it's not going to help too much in this type of machine learning. And I think this is the most simple that I could do. And it's the one that I actually understand the best, which is, I don't know if it can be done a different way. I'm just being honest here. So I'm just using a random forest regressor. I did try 3 other ones, so I'm just borrowing a lot of the code that I wrote for OpenMuscle to see if I can just get something to play with. So we're getting the packets, and in this code, we are able to convert the packet from its original, just a byte object into something that has names, which I do believe the 3D6 edited that code, and I will take a look at it. But let's see if we can get something going today. So let's run serial read one more time. And let's just take one of the data packets from it. We'll just stop it. We can literally take this B data packet and paste it up here. Save it and run it, and this will give us the last packet. List out of range. Okay. uMyo list 0. So nothing was put inside of there, and the parser failed to grab it. Oh, this is code, right? So let me hit Control Z. I'll undo that, save it, and run it, and then it works. So surprisingly, I don't know why there's an O in front of this one. So my computer decided to crash there, which is fine. I love these blue screens of death. So while things are booting up again, luckily we didn't hardly lose anything, because multiple backups. That's why it's good to have a good disaster recovery plan, actually. So this is a good public service announcement. So hopefully my stream came back, but my computer just crashed. So let me load up the files again. Okay, so we got the serial test. Serial read. Hopefully it didn't break my other scene. Did it break my... No, good, good, good. See? It's a nice thing about having stuff set up properly. Okay, so gonna open up serial read again. And let's see why we got that error. That error is actually nice to know. We'll run the module again. Select the port. We get some data. Perfect. So still getting data. Still working. And these might not be individually chunked like this. It's possible that the data is structured differently. So this simple test is going to help us to see if our code filter is going to work. Because we're going to need to filter these packets based off of their timestamp to match them up with the label data. Okay, so let me just run this module. Perfect. It tells us the packet contents. I'm just going to say data2 with 2 A's equals the new string. I'm going to save that. And instead of data, we're going to use data with 2 T's here. And this should parse the data. Okay, good. So now we entered in a new packet, and you can see that it has different values. The battery is at 3880. Before it was at 3850, so it must be slightly more charged. And we do have different values for the data array here. So hopefully, yes, hopefully you can still hear me. And I am super giant. You don't need to see my giant face there. So this is what is inside of the packet. Perfect. So we're gonna want these values here, and these will probably be the meat and potatoes for the machine learning side of things. And what's kind of nice is that it looks like we have 8 sequential reads of the sensor, and I believe that's what it is. And this is a built-in analysis of those, which is kind of neat. So we might want to use the device, the Spectre. I don't know how that's pronounced here. QSG, yeah, pitch, sweet. So I really want to see this, the gyroscope to give some values. So I've placed, what's really cool about this bracelet is this bracelet works super well. So when you kind of fold it over, even for multiple ones, I actually turned the bracelet inside out. And when you do that, what's kind of nice is depending on how big your forearm is, you can use where it folds over on itself as a spot to put the battery. So it's really, I don't know if you guys can see this. So I'm using the static Velcro on the opposite side of the battery to just kind of be sat here in the middle. Sorry again for the camera angle. So there we go. So I only have one turned on right now, but it is turned on. So I'm going to jiggle it. This is a technical term, jiggle. Um, and try to read the data. And I'm going to stop it while it's jiggled to see if I get any gyroscopic data, because I want to make sure that I have the data set up correctly. So we will run this. Perfect. Select COM port 6 was 1, and shaking the crap out of this and hit C. Okay. So there definitely should be some, hopefully, gyroscopic data in this. So now I will change and paste the output from the serial here and run it. Okay, so maybe we might need to turn on the gyroscopic data. That's my guess, because I did move it around. But I haven't read the complete documentation. Okay, so we have these 8. So I'm going to pull up the specs here. Okay, so hopefully I am back. That was interesting. Kicked me out a couple of times. But that's okay. So I have pulled up the uMyo GitHub here. This is pretty interesting. So I don't know. I do not know why my computer decided to reboot, but I do know that I told my OneDrive to not sync for hopefully 8 hours, and it decided to sync back up. So if you're actively hacking me, please stop. Okay, so let me open up a third time, and if the stream crashes, I will start again, probably the later time tonight. Serial read. Okay. And let's open up uMyo data structure. So this is how we are going to be able to take in the data. So one is coming from UDP packets, and the other one is coming from the USB dongle. The uMyo is going to be receiving it. So we're going to have to actually capture both data points at the same time. And I might just have 2 separate Python programs to do that. It is probably not the best way. I should use multi-threading. But multi-threading is a little bit cumbersome, so it's just going to be easier if I just start a new Python instance. Hopefully that will work, but we are going to need to sync the time. So let's see how I can do that. So I'm going to open up the code that I have for Open Muscle for the LASK system. And I think I didn't copy it over. Okay. I will copy it over to the uMyo folder. GitHub, Open Muscle, demo. So we're going to do omcapture.py. So open with IDE. Okay, so last band packet. We are going to change this to uMyo. Last uMyo packet. And this is where we're going to determine the structure. So instead of getting 12 data points here, we're going to get 8 times 4, right? That's 32, because we're going to get 8 packets that match. And what sucks is this method is really throwing out a lot of data unless I can get more. I can't really get much more speed out of my label system unless I compiled it in a different method. So we first have to get a structure. So I'm going to design this in Illustrator. I do most of my design work in Illustrator. But let's see. I do have a pen and paper too. So, okay. So what we have is how many samples per second? So we have uMyo times 4. And each of those 4 gives us 8 data points. And this will have a certain sampling rate, right? So the LASK system has 100 samples per second on each of the 4. And they're just individual. So they each have 1 data point. And I can't spell anything, which is fine. That's why I use auto check. So we're going to get a ton of packets with more data from uMyo. And let's count this. We need to count this rate. How's it going, Joe? So we're going to need to count this rate because we need to know the sample rate. Right, so let's go to the serial. So we can just take the information coming in. So every time it reads a line, we're going to have to start and figure this out. So let me zoom in a little bit here. So this is in our serial read. We need to import datetime. And I'm going to snag another browser. Sorry, I'm closing another needless application. You how to pull current date time, how to get current date time using Python, import date time. Yeah, so current time equals datetime dot datetime now. Okay. So before it starts the loop, it's going to say current time equals datetime dot datetime dot now. Print current time and then input. So we'll F5 that. It's going to ask which device. Oh, it doesn't have any of them listed, so we need to plug it in. Oh my goodness. Ah! Ah! This is why I can't have nice things. There we go. Work smart, not hard, they say. Okay. Now I have that set up there. I think it's because when I have all the different camera angles together that my computer wants to crash, so I'm going to avoid using that scene. I'm going to turn on one of the devices. I'll have to close this shell. Okay, and I want to run it. So now it's working. So it is in COM6, so we can do 1. And so it should tell us the date time, right? Okay. So now I want to calculate the average sample rate that I'm getting. So what we'll do is count every time we're going to have packets equals 0. So every time it prints a line, packets plus equals 1. So the duration we're going to set to 1,000 packets. And then, so print current time. We're going to show the time at the beginning. And then we are going to do end time equals date time dot date time dot now. We're going to print current time, or start time. Start time. And I can't. End time. And then we want number of packets, which of course is going to be 1,000, which is, I don't know why I did this, but you never know, maybe it didn't calculate right, so we're still doing something. Alright, so now we'll F5 it, run it. It's going to run 1,000 times, and we'll see exactly how many packets are sent. I'm also printing this to the screen, so this probably is going to create a lag. So it's gonna make these go slower than normal sometimes. I'm not sure how that works, and maybe 1,000 is too many. So the number of packets is 1,000. Good. Start time is 1637. So open up the calculator. We started at 3.4 and we ended at 23. So 23.8 minus 3.5. It took 20 seconds to send 1,000 packets. So that's crazy. So if we divide 1,000 by 20.3, we get 49 per second. So 49.261. This is actually awesome. This is really good because the number of packets that are coming in, like, so I might have slowed it down again on accident by putting these to the screen, but it gets about 50 packets a second. But in each packet, it has 8 data points, right? So this is cool. So what's nice is I don't think we're going to have to lose any data. We're going to have to throw out some data. Possibly. Because we can't match everything packet for packet. So this is going to be a very fun algorithm, a sort to sort the packets as close together as one another, right? So let's take a look here. So we're just going to call this 50 packets per a second. So 50 packets per second. Way bigger. 50 packets per second. This sends a lot smaller, but it will send 100 packets per second. So these frequencies that we're looking for here are super low frequencies because we're looking at the finger being moving, right, in time. So 0 seconds and 1. So if you think about your finger moving, sometimes you move it fast. Like this movement is super fast, but that would probably be very hard to predict with a machine learning. So we're going to try something simple. We're trying to literally predict this. However fast, fast is okay, but just this press. This is the natural movement of the hand takes a certain amount of time. And so that's kind of the output. The output is the movement that we're trying to predict. So that's what the LASK is for. So for every 100, we're going to have to throw out the LASK values, which is good. Because I thought we were going to have an interesting situation. Because each inside of here, we have 8 packets. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 data points inside of each packet from uMyo. And they pretty much butt up to one another, is my guess, right? So as each packet of 8 comes in, we're going to try to match it with a LASK. And luckily, since we have twice as many of these packets, as you can see that these are twice as shallow, we are going to have to find the one that closest matches it. We're not going to do any guessing. We're going to do real values. So the one packet here that is the closest, we're going to set it to the row for this and cross out the second section. Because ultimately, what we want to submit to the AI, right, is a CSV file. And a CSV file is just a table. So we're going to have on the, this is going to be our labels, and this is going to be our feature data. Our feature data, right? And my thinking is that I don't care. Like, what's kind of funny is the machine learning is it's kind of a cop out because you can just give it all the information and say, "Hey, figure it out," right? So my first inclination is to give it straight up the raw files, in which case it would be 32 numbers. 32 numbers. So there'd be 32 columns, and 8 of them would be grouped together, right? But the machine learning, we won't tell it that. We don't need to. So there'd be 4 groups of 8. I didn't cut this evenly. And then there's just going to be 4 numbers here. We could try that. We can also try to send the, we're always going to have 4 numbers over here. It's our output. We could also send it the 16 data points, 16 the cues, which is I think the spectre. I don't know what the 3D6 calls it, or Ultimate Robotics. The spectre values, which I'm assuming there's some kind of filter there. We could send the 16 and then try to match them here. But I like just the raw numbers, and we're going to actually have to add one. And it's not 5. There's going to be an add one here, and this is going to be our time domain. TD, I don't know what to call it. Time domain. So essentially, we're trying to figure out how many columns that we're going to have. So we don't need to worry about filtering it while we're getting it necessarily right now, but when you pre-process data to train a machine learning algorithm, just remember this. You're going to have to pre-process that data live when you send it to that same model to predict, right? If you're doing any type of real-time prediction, whatever pre-processing you do to the data, you're going to also have to pre-process the data before it gets sent in to the model after it's trained, because it's expecting this format, and you want to give it that format, right? So the architecture of it is kind of important, I believe, right? And correct me if I'm wrong, because I'm just sometimes I feel like I'm going blindly here because I haven't found a whole bunch of material, but mostly I use ChatGPT-4 to help me. So we know that we have about 50 packets per second, which is cool. And we don't, so this is the OM capture. I don't think this one has the hand. Okay. So this one will capture only when both sequences, the last and the band, are connected. So I'm going to do this off stream. So I need to now redo the capture for uMyo to pull in the data from the last and from it. And that's going to be kind of boring, so I'm not going to stream that. But in the meantime, let's just take a look. Let's see here. Yeah, in the meantime, let's just take a look a little bit on the open muscle stuff. I did want just to kind of go through this, because to turn off the open muscle, or sorry, not the open muscle, uMyo, sorry, I get the names. To turn off uMyo, you press and hold the power button until you see the red light, then it will turn itself off. It's super awesome. And these all can be powered off of one lithium-ion battery, but you do not want to power them off of the coin cell battery. The USB device is super easy to use as long as you have the right driver installed, and if you don't, those are prominently displayed on the GitHub. And so I like using this. I might in the future do some other things with actually using a different embedded device to read this, but I'm not that advanced yet, so I don't have any plans for it. Yeah, I do. Let's charge the battery because I do want to charge. I do want to charge the lithium-ion batteries while I'm not using them, and uMyo comes with the battery charger that I haven't used yet. One second. Okay. Did you find a way to turn them on off with one button? Yes, yes. The uMyo turn on and off with one button. You just press it once to turn on, and then to turn it off, you press and hold till you see the LED turn red, and then it turns off. So we have the charger here, but which you should be careful of. No, okay, okay. Yeah, and I also have the wrong side, just JST. But that's fine, because I already have one built in to this, the LASK that I'm using. So I will charge this, charge both of these batteries for tomorrow's stream or whatever stream. I will do this later. And this should be in charging mode. Come on, it should be in charging mode. Yes, but each one by one. When they're connected, you click one button and they all turn on. That's right. You did ask that, didn't you? I wonder, because the 3DS was saying that that might be a possibility. I will work on that actually, Joe. I am going to reread his comments and see what we can do on that end. Because it probably could be software turned on. But the problem is I don't think these are transceivers, so the only way to communicate them is with the button. But you could probably solder a third line onto them. Or make them change the firmware so that they just turn on when there's power. Or maybe you can't do that. I'll refer to what the 3DS said. That's a good. So, and this is the LASK system that I have. Probably not that easy to read, but okay, good. The battery is charging, so it was at 1, but it's charging up. So I'm just going to leave this plugged in. But this is my label device. We'll set this to the side. And then when this one's done charging, I will charge this battery. But I'm going to work on the code to receive both the serial port, serial data, and this is the Wi-Fi UDP data, UDP packet data. So I'm using a socket port to capture the labels and using serial port to capture from the Wi-Fi, or not, the wireless signal from uMyo. And I'm going to try to create the preprocessor. Now this is important, and I didn't know this last time, but, and then Joe says, sorry, my English is bad, but what I meant is, let's say you have 4 connected and I want to turn them on. Do I just click the button on one of them and they all turn on? That's going to be difficult. It's going to be difficult to do that. I will see. I don't know how that can be done because this battery sends a signal to turn it on, and there's no way to tell the device to turn on except for the button. So outside of soldering a new wire, you might be able to, in the firmware, somehow when it gets, no, the 3DS said that you could jump a section actually on the board, and what that would do is that when it receives power, then it would turn on. But if you want to turn on all the devices like that, you'd have to flash the firmware on all the devices and create your own button to then supply the power from the lithium ion. So you'd run into a problem where you're going to have to build your own hardware to send that. Yeah, so it'd be like a relay switch of some sorts. But yeah, you could probably do that. But I think this is just a dev kit for right now, so we're just individually. But that is a good improvement that we might want to make. But I'm not sure. But for now, in its current form, I think it's fine because this is mostly just for experiment, research, and development. But if you wanted to turn this into a full-fledged prosthetic sensor, you would definitely need to do that. But I love this design. I love how slim it is, how easy it is to use. Uh, yeah, it's not in the way. Like even these wires, they are. You could flatten them down, and it feels very well made. And this band it just rocks. So, but yeah, I'm gonna get to work coding. So yeah, pre-processing the machine learning data. So it's very important to get this part right. If you wire them in that, yeah, so they're just gonna turn on when power is applied to them. So the second you plug in power to them, they're gonna be on. Yeah. If you have them all wired like that. Because that's what the 3DS said. You could make a modification on the board so that anytime that they got power, they'll turn on. And the only way to turn them off is to disconnect the power. So that is doable. You can modify your boards that way. But I'm going to leave them as is. But if I find his comment where he said where to solder the board, I can kind of zoom in using my microscope and show that next time. But I do not want to mess with these boards. I'm going to leave them as is because I'm afraid I would break them. It's honestly a great product, and I love that the electrodes are inboard. Yeah, yeah, it's super cool. Again, wonderfully made, super easy to use. Even the battery is super slim. This is separate, of course, but it has everything you need for break. And you can add, I could add 4 more quite easily. And I probably will be buying 4 more, but I want to see how few we can use to discern 4-finger movements. And in the future, I'll be updating the LASK system to include the thumb and more different finger movements. But for now, it's a good way to test machine learning for sensor data. So it is slow progress. I do apologize, but I'll do some of the boring work off stream. And when I have something more exciting, I will definitely live stream. But let me take time to get that coding done. I'm going to take off, guys. But as always, I just want to say, let's see if we can make a positive